Okay. YouTube viewers, hopefully we're back. Okay. And Zoom people, I think we're back. Okay, so what we're going to do is we're going to look at the idea that distance divided by time is going to equal velocity. Okay? So our distance was about 10 meters. And notice that I'm not going to write that as 10.0000 meters. It was about 10 meters. Okay? We kind of laid it out a tape measure. Now, what were the two times?
1.47.
1.47 and
2.
exactly 2.
Yep.
So this is the great out that everybody has. Oh, let's just average the times. Okay? And in this situation, it kind of works. Usually, if you were actually doing a lab, and we actually wanted good data, and you were off by half a second, run that trial again. Somebody is way off. If over this small a time, if you're off by half a second, run that trial again. Okay, but let's take the average. So somebody take 1.47, add that to 2, and then give me that average number. .7 something.
1.735.
Okay, so the oracle says the answer is 1.735. Okay? But this is a situation where my data was only good to the hundredths place. This time can only be good to the hundredths. So I'm going to have to write that as 1.74. So, now, Janine, take 10 meters and divide that by 1.74.
5.7471.
So your calculator says it's 5.74, then what?
71.
Okay? Meters per second. So the oracle has spoken, and this is what your calculator says the answer is. Now, here's the problem. If you write this, and this is what I look at, I'm going to think you had really, 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 really good data. Okay? I'm going to think, wow, I don't know what you guys had, but this is amazing. Okay? To time an old physics teacher as he runs down the hall. Eventually, if I teach long enough, I'm going to be long enough, like pushing this thing with a locker and go, okay, start. You know, come back later. I'll get back with you kids. Okay? You know, you guys go get a snack by the time I get down to 3 meters. So if I get to that point, if you ever are on YouTube and you randomly are looking at this and you see Berkamp like pushing a stroller, doing this, make me stop, okay? Come back, have an intervention and go, Berkamp, give it up, okay? The stroller races, no. You've done your time, go. Okay. But here's the deal. If you look at this, I can't make this look better than what I've got. So the 10 meters had 3 significant digits. This had 3 significant digits. I'm dividing, so how can I write this velocity? 5 point what? 3 significant digits, 5.75. So 5.75 meters per second. Now, to give you some comparison, if you are a world-class sprinter, Usain Bolt, you're going to run the 100-meter dash in about 10 seconds. If I was a world-class sprinter, that would have taken me 1 second to run that 10 meters. Okay, if I was a world-class sprinter, which I never have been. But if I was a world-class sprinter, it would take you that amount of time. Now, if you're going 120 kilometers per hour, and that, again, this is one of the conversions that you have to be able to do in your sleep. 120 kilometers per 1 hour, okay, conversion from kilometers per hour to meters per second. You have to be able to do this without a second thought. Put 1 kilometer down here, put 1,000 meters up here, put 1 hour here, put 3,600 seconds here. These cancel out. You multiply by 10, and you divide by 36. Okay, this is the same step every time. This is the most common conversion you will do in this class, is kilometers per hour to meters per second. multiply by 10, divide by 36. So you'll always get an answer smaller than what you had. So you do the math, that works out to be about 33 meters per second. So like the African country that I was at in Botswana, this was the speed limit on the highways, 120 kilometers per hour, which is roughly about 70 miles per hour, roughly, okay? Which is 33 meters per second. So what you guys have to get used to is that you all aren't used to thinking of velocity in terms of meters per second. If I say, hey, somebody throws a 90-mile-an-hour fastball, you guys get an idea of how fast that is. Or you're going 60 miles an hour. Oh, okay, right, you have an idea of how fast that is. Meters per second, you all aren't used to thinking about this. So I'm going to do this just so you can get an idea of some different velocities in meters per second. So 5.75, that's a 54-year-old physics teacher running down the hallway, okay? Not all that fast. Here's a fast car, about 33 meters per second, okay? Now, the speed of sound is 343 meters per second. So, if you're going to travel if I was going to run at like the speed of sound, I'd have to run a lot faster, okay? Okay? I just didn't want to show off and break the sound barrier, but the physics teacher breaks sound barrier, windows shattered at Mays High School. So, but this is the sound barrier, 343 meters per second. So unless it's a bullet, a high-speed plane, a satellite in orbit, this is kind of like a speed limit. So if you ever get a velocity faster than the speed of sound, ask yourself, is this something that's reasonable? Can this thing go faster than the speed of sound? Okay? So if you're calculating the velocity of a Toyota electric car hybrid, as it goes up, accelerates, and you get this thing going like 500 meters per second, you've done something wrong, okay? This is not going to break the sound barrier. So just be cognizant of the speed limit. Now, the ultimate speed limit is the speed of light, which is 3.00 times 10 to the 8th meters per second. Now, to give you some idea of how fast that is, let me get a prop right quick. And this is one of the calculations that you're going to do on the assignment for today. If you could stand at the equator, okay? So right here, say close to Nairobi, Kenya, that's pretty close to the equator. And you turn on a flashlight, and you send that beam of light around the Earth. So in other words, instead of going straight, it would exactly follow the circumference of the Earth. It would take less than 0.2 seconds for that beam of light to come all the way back around to where you're at, to give you some idea of how fast that is. So it would be like me turning on the beam of light, and about how long it takes for me to snap my fingers, that beam of light is going to go all the way around the Earth and come back to me. From the time that I turn it on, snap my fingers, that beam of light has come back. That's all the way around the Earth. So if you ever get a velocity faster than the speed of light, you have done something horribly wrong, okay? Even if you get something approaching the speed of light, if you get 10 to the 6th, 10 to the 5th, whatever, meters per second, and that's just like an electron that's being accelerated, it ain't happening, okay? It's not going to happen. So I just give you these numbers so when you begin to get answers, you can look and go, wow, do these values even make sense? Okay? So, speed of light, 10 to the 8th. Speed of sound, 10 to the 2nd. Fast cars, 33. Old physics teachers, about 6. I'll round up and I'll give myself 6 meters per second. Okay? And if I had done the 1.47, it really would have been fast. Okay? I think somebody screwed me on timing it at 2 seconds. I think he was slow in the reaction time. Okay. But of course it was that fast, I could understand how you might be off. All right. So, one of the things that you can look at is that I happen to have Albert Einstein here. And we're going to swing Al around in a circle like this. Okay? So as Al's going around in a circle, I want to determine how fast Al is moving as he goes around. So what we're going to do is that here we are, here's Al, right? Al's going around in a circle. So at the end of the day, I want to use the idea that t equals some distance divided by, excuse me, I'm sorry, I screwed that up. Hold on, let me back up. That the velocity is going to be some distance divided by time, okay? Just like I did when I was running, but this is, imagine me running around in a circle. So when something's moving in a circle, and you're going to come back to that same point, first off, quick refresher of geometry. How can I find the circumference of that loop? How do you find the circumference of a circle? 2 pi r? Everybody cool with it? Okay? So the distance Al is going to travel is going to be 2 pi r. Now, because he's going to come back to the same point in the circle, I'm going to use uppercase T. So when I was out running, I used lowercase t because that was just one time interval. I wasn't coming back to that point. Anytime you use uppercase T, that's going to be the time required to come back to that point. So it could be Al going around in a circle. It could be the Earth going around the sun. It could be our star, otherwise known as the sun, going around the Milky Way galaxy, because our star is part of a spiral arm that's going around the Milky Way galaxy. So anytime something's going to come back to a point in a circle, you use uppercase T, which is going to stand for period. This is just getting you the radius, so this will get you the circumference, and this is how long it's going to take. So don't look at this and go, ooh, that's a really fancy equation, 2 pi r over t. All this is distance divided by time. 2 pi r just tells me how far I travel. The uppercase T just tells me how long it's going to take. Yeah, you guys still have the stopwatches?
Yeah.
Okay. So I'm going to get Al moving, and I want you to try and guess kind of how long it's going to take Al to go around. Okay? Just one time. So let's do this. Let's count 10. I'm going to tell you guys to start. I'm going to count 10 revolutions. So we're going to time 10 revolutions, and then we can find the time for one. Okay? So I'm going to tell you guys when to start. Go. Stop. So what'd you get?
6.69.
I get 6.87.
Oh, that's not bad. See, you guys are better at that than me running 10 meters. So you got what, 6.7, and you've got roughly like 6.9?
Yep.
So let's call it 6.80. Okay, kind of close. Now, as far as the radius goes, okay, we're about like this. Let's call that about a half a meter. Okay, 0.50 meters. That's pretty close. So if I want to figure out how fast Al is going, I'll take 2 pi times a half a meter. And what was that? That was for all 10, was like 6.8. That's kind of the average.
6.69.
And you had?
6.87.
So somebody take 6.69 and 6.87 and add those two together and give you that average.
$6.78.
6.78 seconds. Okay? So, but that was for all 10. So the time for one, how are we going to get the time for just one? Divide by 10. So we're going to use 0.678. So somebody take 2 pi times a half, otherwise known as pi, because a half times 2 is 1. So take pi and divide that by 0.678.
$4.6336.
It's 4.6336.
Yeah.
Now, can I write that out like this? Can I write this as 4.6336? No, because if I see this for my velocity of owl, I'm going to think you all had some phenomenal data. This has 2 significant digits, right? Guess what? My answer can only have 2 significant digits. So how am I going to express this velocity? 4 point.
6, 3.
Yeah, no, I can only have 2 because this only has 2 significant digits. So I can only write that as 4.6 meters per second. So this is, I do this just so you can realize, like, man, we had some really kind of sketchy data on the radius. That limits my answer. I can't go, oh, 4.6336 meters per second. I don't have that good of data to express that good of a calculation. Okay, stand up, take a stretch. I got one more big problem to work, and then I'm going to turn you loose. I've lost it. I get a sheet of paper with this.
This is surprisingly difficult.
I don't have that much in.
Oh, yeah, sorry.
You got it.
Yeah.
Okay. So, we got one more velocity to calculate, and then you'll hopefully by now get an idea. So, Jupiter has an average radius of 7.781 times 10 to the 8th kilometers, and it takes Jupiter about 12 years to make one loop around our star. So if you like birthdays, don't live on Jupiter, okay? Because if you look at a birthday as being like when you come back to a certain point and complete an orbit, you're only going to get a birthday every 12 years. So the good news is, like, the legal drinking age is like less than 2 years. It's like, how old do you have to be to drink on Jupiter? About 1 3/4 years. Really? Nice. Nice. Okay. So, it's like, you're an old man if you're like 4 on Jupiter. Okay. So I want to calculate the velocity of Jupiter. So, in reality, Jupiter moves and all planets move in elliptical orbits. We're just, for the sake of argument, we're going to assume that it's a circular orbit. So, how can I figure out how fast Jupiter is moving? I'm going to use the same idea that I did with Owl. But now, listen to me very carefully. I want the velocity of Jupiter first in kilometers per hour, and then I want the velocity of Jupiter in meters per second. So, what can I do?
Convert years to hours.
Well, no. Okay, you're like on step 3. Okay? I want step 1. At the end of the day, I got to figure out how fast Jupiter is moving. So what 2 things do I need to know?
Distance.
I need to know
Distance.
how far it goes and
How long?
time. Okay? Just like when I went out there and ran in the hallway. I needed to know how far I ran and how long it took. So Jupiter is going to be moving in the circular orbit. So again, how are we going to find the distance Jupiter is going to move? What are we going to use? 2 pi R, right? So we're going to go, okay, we're going to have 2 pi r divided by t. So we're going to have 2 pi, and then that radius is 7.781 times 10 to the 8th kilometers. Okay? Now, so if I just crunch this number up here, this is going to tell me how far it goes. That's all. That's what it's going to tell me. And it's going to be a big number. Okay? Now, when you're doing this, I am a stickler about showing work. I don't do this. I don't need to show, you don't need to calculate this number separately and then write it down. And then take 1 year and convert that into seconds or hours or whatever it is, and then write that down and show me those individual steps. I don't need that degree of detail. I just need to see, hey, this is how you're going to do it. Then I'm going to take, the orbital period was 12 years. Now, notice I want an answer that's in kilometers per hour. So I'm going to take the years and do what? Change the, I just have to convert it into hours. So 1 year, what can I do with the 1 year? 1 year is what? 365 days. Technically it's 365 and a quarter, but we're just going to call it 1. So 1 year, 365 days, and then 1 day is 24 hours. Okay? And it's weird, actually the Earth is slowing down as it spins. Okay, not a lot. But a day used to be less than 24 hours. Actually, they think when the Earth first formed, a day was actually about 12 hours. Okay? So imagine that was like, oh, yeah, you'd have 6 hours, you know, instead of taking 24, it'd be like 6 hours or 12 hours to go around. Okay. So this is all I need to see. I don't need to see what you get out of this by itself or this by itself. Now, what you do from here is up to you. How you handle this mathematically on your calculator is up to you. If you're going to do this, first off, when you do this times 10, listen to me very carefully. Don't punch in times 10. You should have like an EE key on your calculator, because if you type in times 10 to the 8th, it's going to completely screw up your order of operations. Okay? So be very careful about this. Don't type in times 10. Sometimes it's a second function EE, but that EE takes the place of the times 10. So now down here, again, I don't care how you do this. What some people will do is they'll calculate all this on top, and then they'll divide by 12, hit enter, then they'll divide by 365, hit enter, and then they'll divide by 24 and hit enter. Okay? If you like that, hey, go with it. That's cool. The other option is that you can enter all of this and then put this in brackets, divide by, and then put all of this in brackets, 12 times 365 times 24. This is all up to you. Okay? I don't care how you do this. But make sure everybody can do this, because this is what you're going to have to do on your assignment today. So if you want to, I want a couple people to do this calculation so that we can make sure everybody's got this going on. So somebody do this calculation. Take 2 pi times 7.71781. I'm sorry, I left out 8. Hold on. 8. And then divide that by 12 times 365 times 24. And technically this is 12.0 years. So that's the smallest number of significant digits. So here's what I want. I want an answer in scientific notation to 3 significant digits. Is it just me or is it hot in here? So what'd you get?
802.29.
So so 3 significant digits in scientific notation would be what?
8.029.
Three significant digits are just 8.02 times 10 to the what? Oh, go away, that number.
To the second.
8.02 times 10 to the second kilometers per hour. Is that what everybody else got? That seems small. It could be right, but it doesn't seem right. Party girl, what are you getting?
I've gotten two different numbers now. I'm on my third try. I'll get
Okay,
back to you.
this is why I want you all to do these calculations, because this is what you're going to have to do on your assignment. So I've had, were either one of them 802? Okay, so here's my point. I've had, Party Girl did the calculation twice, okay? You did the calculation once, and you all got three different answers using calculators. This is why I want you to do this, so that you can make sure that you can do it when you get home. Anybody else get an answer? What'd you get?
4.65 times 10 to the 4th.
Times 10 to the 4th kilometers per hour. Okay? So we got a little bit of variation. We're off by an order of magnitude of 2. Okay? 10 to the 2nd versus 10 to the 4th. Okay? That's like off being by like 100 minimum. Off by like a factor of 100. I'm not talking like, oh, 100. I mean off by a factor of 100. Yes?
I did it again and I got the 4.65.
So are we feeling good about this one then? Party girl?
Yeah.
Okay. Rachel? Or is the verdict still out? Good? Rachel? Or are we hesitant? I feel like I'm frozen in time. Got it?
Sure.
Okay, let's go with it. Okay. So, 4.65 times 10 to the 4th kilometers per hour. Now, let's change that into meters per second, because this is what you're going to have to do on your assignment. So, what I would recommend, do this. Stack that over 1 hour. Okay, because this is what this means. This is how fast, how far it's going to go in 1 hour. Then do this and go, oh, 1 kilometer is 1,000 meters, 1 hour is 3,600 seconds. So you can lock off those zeros. So here's the short version. Take this answer, multiply it by 10, and divide by 36. Now, what I would do, because you all have calculators that store stuff, what you got out of this, and you're going to do this next conversion, you could actually, if you have this whole number in your calculator, just keep that number there and then just multiply by 10 and divide by 36. If you still have that number there, you could write down this answer, but then when you use that number in the next calculation, just keep that whole thing and then multiply by 10 and divide by 36. So what do you get in terms of meters per second? 3 significant digits, scientific notation.
.29 times 10 to the 4th.
Meters per second. Now, out of curiosity, take that number and divide that by 343. What'd you get?
37.66.
So, about 38. So what that means, this is about 38, Jupiter is traveling through space at about 38 times the speed of sound. Okay? That's really fast. Now, the beauty of outer space is that it's a vacuum. So it can go that fast because it's not being slowed down by traveling through an atmosphere. But yeah, if you're on Jupiter, you're along for the ride. You're traveling 38 times faster than the speed of sound. Okay, that's how fast Jupiter is going around. Okay, so let me hand out your assignment. That's going to be due tomorrow. Find it.
Do you want the dimensional worksheet handed in or it's turned online?
No, everything gets turned in through CamScan.
All right.
Yeah, because that way I don't have to keep track of what's been handed in. Yeah, everything gets turned in through CamScan. Everything gets turned in through CamScan. Okay. So, let's talk. So, this is kind of a summary of everything that we've done. So, let me kind of get you through this question about precision, accuracy, okay? So, let's say that you have a measuring device that's marked off like 0.1, and then you have another mark at 0.2, and then you have another mark at 0.3. And you're going to measure something, you're going to measure a chunk of wood that's like this long. So, here's your measuring device, here's 0.1, here's 0.2, here's 0.3. What would you say the length of that stick is?
0.28 or 9.
Okay, right? Call it 0.28, okay? So here's the deal. Are you certain that that 0 is correct?
Yeah.
Are you certain that the 2 is correct?
Yeah.
What about the 8?
No.
That's your guess. So when you look at a measurement, the last digit is, this is where your uncertainty is. That's a guess. Your first digits are known, whether that's a digital scale, whether it's something you guys are going to measure or whatever. Even when you looked at your time, when you guys were doing that time and you had 1.47 seconds, the 1 and the 4 were known values. That 7 is what the timing device estimated, and that was kind of, oh, this is what we think it is. So when you're looking at a measurement, the last digit's a guess, the first digits prior to that are known values. Now, when you get to question number 4, okay, you've got x equals kv squared. So this is the stopping distance here. Here's your velocity. This is the value of k. So what you want to do on number 4, and this is a process, you want to use dimensional analysis to figure out the units of k. All right, that's what you want to do. You're going to use dimensional analysis to find the units of k. This is a process, okay? So come in here, that's a distance. You're going to have meters, you're going to have k, you're going to have meters per second squared. So what you want to do is